Hello, everyone. My name is Ray from MIT CSAIL. I just finished my PhD at MIT this summer, and I'm currently a postdoc. Today, I'm presenting our work in multimodal representation learning via maximization of local mutual information. Clinical data is often multimodal. They reflect different yet correlated manifestations of a subject's underlying physiological processes. We aim to improve computer vision models that infer the underlying diagnosis or disease stage from medical images. In particular, we improve the image model by learning the latent feature representation Z generated by the same pathology Y and shared across the multimodal clinical data. As an example, if a patient has pulmonary edema in their lungs, and we aim to infer this pathology from their chest X-ray image, we want to train an image encoder that extracts the relevant radiographic features. In this case, we can leverage the text in the associated radiology report that describes the same patient's pathophysiological processes and encode the corresponding features from the text into the representation space. Now the question is how to capture and formulate the correspondences across those two modalities. The measure we choose is mutual information. Mutual information quantifies statistical dependencies between two random variables, both linearly and non-linearly. Specifically, we encourage the image and the text representations to exhibit high mutual information. Furthermore, we leverage the local structure of image and text data. Here's an example. We have a chest X-ray image and a radiology report written to describe the findings of this image. The first sentence describes a finding in the left lower lobe. The second sentence, although describes the absence of pathologies, is still focused on one local region, the left lung. We observed this pattern where a sentence is usually a minimal and complete semantic unit. The findings described in that semantic unit are usually captured in a local region of the image. So we propose to maximize the local mutual information between image and text features. Here's how it works. We first encode an image into a batch of local image features and encode a sentence-level text feature. The image encoder is a residual neural network parameterized by theta EI, and the text encoder is a BERT model parameterized by theta ER. Then we apply a mutual information estimator to estimate the mutual information between the batch of image features and the sentence level feature. We experimented with two popular estimators, MINE and CPC. Both estimators apply a neural network discriminator parameterized by theta ED to approximate the lower bound. Among the estimated mutual information values, we select the highest one. Then we optimize this highest local mutual information term by back-propagating through the image encoder and text encoder. Essentially, for each sentence, we select an image region that has the highest mutual information with it to optimize. The reason we have this one-way maximum is that a sentence in a radiology report was usually written to describe either the presence or absence of an image finding. The image region that has the highest mutual information value will be most likely where the sentence was trying to describe. Finally, where the downstream task is imaging classification, we fine-tune the image encoder followed by a classifier to perform image classification. We tested our methods on pulmonary edema assessment, as well as detecting other 9 pathologies. All the numbers are reported in our paper, and I don't expect you to read all of them in this video. But the highlight here is that local mutual information to learn joint image text representation leads to the best performance in most downstream image classification tasks, compared to applying global mutual information or the image-only model. Finally, I'd like to emphasize the 3 advantages of optimizing local mutual information. 1 is a better fit to image text data structure. 2 is a better optimization landscape due to its lower dimension. 3 is better representation fit to downstream classification tasks. If you're interested in our work, feel free to reach out via email. Thank you so much for your attention.